Hi, and welcome here to our session at GTC21 on arming your Jetson Nano with Tony Stark superpowers. My name is Jongboom and I'm the co-founder and CTO of Edge Impulse. And in the next 40 minutes, we're going to be showing how you can make your Jetson Nano feel, hear, and see the real world. This is going to be super interesting. We're actually going to be taking our Jetson Nano for a spin, building real models right here in front of you. So, super excited. But first, I want to show a little bit of background and how I arrived at this point of actually starting to do embedded machine learning on these types of edge devices. So for me, 2017 was really a pivotal moment. I was an embedded engineer working at ARM. And for me as an embedded engineer, kind of where my engineering stopped was the moment that we delivered a device or wrote some of the embedded software where we collected some data, made it really battery efficient. But what happened with that data was largely ignored. But there's also a completely separate industry of people that are sitting on the other side of the fence, looking at the data, but never actually looking at the devices that collect that data from the real world. In this case, these were data scientists and mathematics students, PhDs and master students, that were studying in East Africa and that attended the summer school, Data Science Africa, in Tanzania that year. So for me, this was the first time that these two worlds actually combined. I was there as the designated IoT specialist, showing these students on how you can actually collect data from the real world and show them how all that data in their MATLAB scripts or their IPython notebook was actually collected, and how you have your feet in the mud to actually do that. And they showed me what we can actually do after we collect that data and how much incredibly valuable information we can gather from the real world once we start combining our two industries. This was fantastic. Together with 60 students, we were running around on a dairy farm. We realized that cows do not move a lot, except if you actually keep them in a small enclosure for about an hour, then they run really fast. So I was there with a laptop in my hand, running after the cow, students noting down what the cow was doing, all about trying to build a model that could accurately predict when a cow was getting sick or when a cow was in heat. Two problems that are really, really precarious for dairy farmers in Tanzania. So super awesome. And this really inspired me to start thinking about how embedded developers can start learning to use machine learning to start understanding a lot more of the world. Because if we look back over the last 10 years, kind of from the first moment that the Internet of Things term was kind of coined and everyone was promising that there will be billions of devices that could sense the world and give me some understanding of what's happening, we've seen the volumes actually come here. Over the last 4 years, ARM has shipped about 100 billion devices, more than in the 25 years prior, which is an astonishing amount of devices. This year alone, there will be 30 billion chips being shipped with ARM tech inside of them. And that's not even all the chips that are there. It's an astonishing number of devices. But if we actually look at what they do, I'm a little bit disappointed. A lot of these billions of devices are being solved to solve real problems, absolutely, but relatively simple problems. Stuff like cold chain monitoring, which on itself is an amazing use case. It's fantastic that if I'm at a beer factory, I can know what the exact temperature is, and to make sure that the temperature of my product over the complete life cycle of that product never is above, let's say, 4 degrees Celsius. But it's a relatively easy use case. And why do we choose these types of use cases? It's because they're straightforward to implement. I can just buy an off-the-shelf temperature sensor, connect it to a dev board, and bam, I have my very first prototype temperature sensor. This is really great. However, there are way more interesting problems that our IoT solutions were promising to solve, but are not solving at the moment. And the reason is that it's much harder to solve them with our current technologies. Think of an elephant walking on the African savanna. If I want to know whether that elephant is present in a certain area, I can't just buy an off-the-shelf elephant detection system or even a sensor that I connect to my dev board. No, I need to rely on normal senses. Maybe vibration, I can probably feel an elephant coming, maybe based on sound, maybe you can hear an elephant, or even on images or thermal images to see whether an elephant is there. But because of this wide variety of ways that I can actually detect this makes it incredibly hard, especially if you consider all the other noise that we see throughout us. There are infinite number of sounds, there are infinite number of images and maybe even an infinite number of vibrations all around us all the time. And trying to detect the one thing that you're interested in is incredibly hard. Think about all the different sounds that you could be hearing right now, and then write an algorithm, just by hand, doing normal coding, to detect whether glass is breaking or you hear an elephant trumpeting. Really, really hard. But this is where I think by far the most valuable things are in this IoT space. Because if we no longer just can detect stuff that our off-the-shelf sensors can do, but rather can write code or make machines that can detect anything that we can do with our primary senses, all of a sudden we can start covering much higher value use cases and really start understanding the world. But that's hard. And the reason why it's hard is this infinite number of inputs. If you're writing a normal system, if you're just programming out a control loop on an embedded system, you'll start with inputs. And in the case of, let's say, a cold chain monitoring system, that's relatively simple. You have a temperature sensor. It's a single input. It's probably not even very high resolution. If you sample every 10 seconds, that's probably good enough. Then you'll write a control loop, your application logic. And then finally, there's an outcome. But if your number of inputs is infinite, then it's very, very hard to actually write a proper control loop that can distinguish between all of these things. Even more so if you consider the incredibly high frequency and high resolution of a lot of our senses. If I listen to audio, there's probably 16,000 values already coming in if I'm sampling at 16 kilohertz. With images, there might be 240 by 240 pixels being bombarded into my eyes 10 times a second. How to actually write an algorithm that can properly distinguish between seeing an elephant or seeing something completely different. Now, fortunately, there's another way of writing our software. If we can't figure out these rules, if we can't figure out the correlation between the input and the output ourselves by writing this out, we can use machine learning. And I don't think of machine learning as a magic black box where you throw some data in and magic numbers come out or a magic conclusion comes out, but rather as an engineering tool that when you have this very specific problem where it's really hard to find the rules, you can collect lots of input data, collect lots of outcomes, stuff you want out from there, and a machine learning algorithm can then actually find that hidden correlation between input and output. The mathematical rules that make up this algorithm, it can do that for you. I think that is really powerful. And from that, machine learning is really widely applicable in a very wide variety of use cases. If you have audio data that you want to analyze in real time, machine learning can help you find the rules from going from a waveform to, do we hear an elephant trumpeting? It can go based on image data. It can actually take a picture and map the values of those pixels back to an outcome. Do I see a poacher, yes or no? Or even on smaller devices, in industrial maintenance, for example, do we see abnormal vibration patterns? If you look at biosignal analysis, machine learning is a really efficient way, or is a way, basically the only way, to actually accurately map data from, for example, your bloodstream to sleep phases. Anything where you want to do, basically any place where you have really high resolution and messy sensor data, that when you plot it out in Excel, you can kind of see that there is a correlation, but you can't actually write that out in code. That is a place where machine learning can help. Now you might wonder, Jan, yeah, it's amazing that machine learning can help, and I've heard so much about fantastic systems beating professional players in Go, but machine learning, isn't that data centers full of GPUs? Well, sure, that is where a lot of machine learning happens. But I want to show you that machine learning is not this magical thing running in the cloud, but there's fundamental mathematical principles underpinning machine learning that actually allow us to run this even on edge devices. And very often a machine learning algorithm doesn't even need to be more complex than something you would write out yourself. So let me show you based on a small example. Let's say that you're an embedded engineer tasked with writing a control loop for a device that can detect whether water is cooking. So what do we need? Well, a pot of water and a temperature sensor. And as I know, I've been to primary school, water is boiling above 100 degrees Celsius. So my control loop, I write out, if my temperature value is above 100 degrees Celsius, the water is boiling, otherwise it's not. And this is great. I test this out in the field, I bring the water temperature up to 102 degrees, and yeah, according to my algorithm, this water is boiling, and I observe that it's boiling as well. Now I do the same at 98 degrees, and according to my algorithm, the water should not be boiling. I observe the water, and indeed it's not boiling either. This is perfect. But then I go mountain climbing, and I'm at 2 kilometers high, and I bring the water temperature up to 98 degrees, and all of a sudden my algorithm says that the water should not be boiling, but the water is. Now we know that there's a hidden correlation between the altitude that we are, because that's the only variable that we changed, the temperature, and the boiling temperature of water. So if we can't actually find that correlation ourselves, that is a moment where machine learning can help. So instead of trying to figure out these rules ourselves, we're just going to write down a number of data samples. So in our case, our inputs are the temperature and the altitude, and our observation, our label, whether water is boiling, yes or no. And we do this for a wide variety of altitudes and temperatures and the observation that we make. And in essence, you create a large spreadsheet, what you see here behind me. Now we can let a machine learning model loose on this data. So a machine learning model doesn't know anything about what temperature is, what altitude is, or even what water is. All a machine learning model does is trying to find a mathematical formula that best maps the inputs to the desired outcome. And it will try to do this as close as possible. But the only actual calibration that it has is based on your data. So the quality of your data directly has an influence on the quality of your machine learning model in the end, or the quality of this formula that it finds in the end. And this takes lots of trial and error, because the machine learning model or the machine learning algorithm has no idea what each of these things mean. It just tries to find the mathematical formula that best maps the inputs to the outputs. But after it's done, it's just math. It will probably find a formula just like this. And this is a formula that you can find in any textbook for the boiling temperature of water. There's no difference between me as a person finding that model or the machine learning algorithm finding that model. Just the process is different. Rather than trying to deduce the correlation between these two things, we'll have a machine learning algorithm do that. And the key here is, the one point that I'd like to take everyone away from this session is machine learning is just math. There's nothing special to it. It's a mathematical formula that a machine learning algorithm finds. And after the machine learning algorithm is done, it's just math. And computers are incredibly good at math. Even a small microcontroller these days, like a Cortex-M4 running at 80 megahertz, is capable of doing 40 million instructions a second. So even if this mathematical formula has hundreds of thousands of parameters, which is really hard to grasp as a human trying to write that formula out, but is an easy task for a computer to do so if you're doing, for example, audio analysis, we can do this in a fraction of a second on relatively underpowered hardware. And that is really, really cool. So this is what makes it all possible. But how do we actually go and actually build a model? For me, there's 4 stages of doing that. The input data, so both your raw data as well as your observations, are by far the most important aspects of your machine learning model. You need to have high quality data, preferably input data at the highest resolution possible, and really good observations. Mislabeling data, if you, for example, have a lion roar and you label it as, oh, this was an elephant trumpeting, that will have a deteriorating effect on the quality of that formula that it finds and the accuracy of your network. So first, start with raw data. Then, from the data, I'd like to actually look at what can we extract from this data without machine learning. Very often, you'll learn relatively quick things about this without ever having to do anything with ML. For example, here I have some data from an accelerometer. And it's very noisy, and that's because an accelerometer is a very noisy sensor. If I use some signal processing techniques, stuff that we've been doing for the last 40 years, it's not that on-device intelligence is anything new. We've been doing that for a very long time. I can just apply a low-pass filter and go from this really noisy signal to something very, very clean. And if I clean it up already beforehand, that means that my input data is of much higher quality. All this noise doesn't need to be removed by any algorithm. I think that's really cool. Similar, if I have a waveform, semi-elephant trumpeting again, I can take that waveform and actually turn it into a spectrogram with time frequency domain features, which denoises the signal and gives me a much clearer picture with much less features, much less input data, where a machine learning algorithm can do a much better job. So, and just to demonstrate how that actually affects the quality of our data, here is some raw data of me doing a fist bump, me doing an up and down movement, and me drinking a beer, all with a sensor attached to my hand. So on the left, you'll actually see these three distinct motions, and they make a lot of sense. Like in orange, I have up and down, where there's lots of energy in this axis. And when drinking beer, I have lots of energy on this axis. But it's really hard for me to find any single one of these points, say somewhere in the middle, and then ask you, do you think this belongs in either the fist bump, the beer, or the up-down class? You don't have enough information. It can be anything. And thus, a machine learning algorithm will have a lot of trouble finding the best correlation as well. By just applying a low-pass filter over this data and then doing a fast Fourier transform, kind of finding where the peaks in the signal are, we can already start separating this data super nicely even without doing any of the machine learning. And thus, a machine learning algorithm, or even someone writing a controller by hand, will have a much, much easier job doing that. So incredibly useful. So once we've cleaned up the data and we've verified that the data makes sense, we can let the computers figure it out. For me, I think there's kind of three real standard classes of machine learning. Classification, so what is happening right now? You can think of this as, do I see a poacher or do I see an elephant on an image? Anomaly detection, is what I'm seeing or what I'm hearing or what I'm feeling out of the ordinary? Do I hear something that I never heard before near a sensor? Because that might be an indication that something weird is going on and I probably want someone to actually look at it. Or regression, and that's kind of predicting the future. Based on the historical data that I have, what do I think the temperature of my cold chain monitoring system is going to be an hour from now? And then finally, we want to deploy this back to the device, because no one has anything about this ML algorithm if it just runs in the cloud somewhere. The real power of these algorithms is if we put them back on one of those 30 billion of MCUs and MPUs that shipped this year. So why we do this is we take all your signal processing code, all your machine learning code, and we wrap that up in a C++ package and then give that to you. And from there, it's just mathematics, as I said earlier. And as I also said, computers these days are incredibly efficient at doing that. So from here, we can start deploying this on a wide variety of devices. And this does not have to be a full-on Jetson Nano, right? For a lot of use cases, you can actually deploy this on much smaller models or much smaller devices. So we see this as kind of, as long as it's math, you have a lot of control in the complexity of that formula. So we can see devices being deployed from Cortex M0 Plus for basic anomaly detection, to Cortex M4 devices for full-on audio classification, to Cortex M7 and low-class Cortex A devices to do image classification, all the way to a Jetson Nano doing full object detection. But naturally, it also means that the Jetson Nano is capable of doing every single one of those use cases, which makes it a fantastic starting point to actually do that. So I have a couple of actual numbers here, performance numbers here, and showing that you can do real-time anomaly detection on accelerometer data, even on a Cortex M0 Plus running at 48 megahertz, in about 10% of the duty cycle of the CPU. That's really cool. So the brilliant thing, I think, here is that once you start collecting that data, once you start looking at the data and extracting some interesting features, you can already decide, okay, well, based on what I see here, the mathematical formula that I need to actually map these inputs to this output, I can actually run on an M4 maybe, depending on the complexity, or maybe here I need Cortex-A. And knowing those device constraints while you're designing the system, rather than trying to figure this out later after you have a working model, is really great, because it allows you to design exactly for the thing that you actually need to target. And that's where I think lots of real power comes in. So I hope you guys are really excited about this kind of thing and then have an idea of the value that machine learning can really provide. So how do you get started with all of this? Because yeah, it sounds exciting, but it sounds a little bit complex as well. So enter Edge Impulse, the company that I co-founded. We're the place to build embedded machine learning models. And we are an engineering tool. We're not a magic black box where you throw some data in, you press a button and you get a model. But rather we help you collect data from your devices, because I feel that that is where the value is. There's not a lot of value in just going to a model zoo and downloading a model and then trying to make that usable. Machine learning really starts shining when you plug in your own data and start solving your own hyperlocal problems. It's a tool that is there every step of the way, from initial data collection to extracting interesting features from the data, to training ML models to actually extract value from those features, all the way to deploying these back to device. So for the Jetson Nano, we've added really easy bindings to collect data from microphones and cameras, but with a few lines of code, you can get data from accelerometers, temperatures, sensors, gyroscopes, essentially anything that you can think of. And Edge Impulse is also the largest community of embedded ML enthusiasts. We have today, actually the moment that we record this, over 16,000 projects, real ML projects with real data in there, 14 million labeled data samples. It's absolutely astonishing. And just in the last 21 days, you, the community, added 4 million labeled data samples here. So if you want to learn about this, go to edgeimpulse.com, sign up and get started now for free. And the really interesting thing here, why we're here today, is the amazing new stuff that we've done with the Jetson Nano. So from today, you can use your Jetson Nano every step of the way to build these type of ML models. The only thing you need to do is grab your Jetson Nano, connect it, and run our small install script. It runs in a few minutes. And after that, your Jetson Nano is the perfect device to do data collection. The Edge Impulse Studio will then help you analyze the data, extract interesting things from the data, and then you can deploy that back to device. We have high-level SDKs actually in JavaScript, Python, Go, and C++. So really easy to get started and modify that. We're going to show that in the demo in a little bit. And we run on the Jetson Nano with full hardware acceleration. So we're using TensorRT, NVIDIA's library, to run neural networks much faster on the GPU. And you as a user don't even see that. You just invoke the model, add a couple of lines of code to interact with the model, and you're ready to go and actually start providing real value for your specific use case. So in the docs at docs.edgeimpulse.com, we have end-to-end tutorials on predictive maintenance on accelerometer data, detecting gestures, doing stuff with the radar. Really interesting, especially now in COVID days where you can't touch anything anymore. You can just make a gesture in the radar and it will detect that. Keyword spotting, non-voice audio recognition. We'll do a little bit with bird classification in about 2 minutes. Image classification on normal images, and even object detection, what you can run on your Jetson Nano. And for me, this is where everything comes together. The moment that you give your domain experts and your engineers, as I said, this is not an ML tool, it's not a tool for data scientists, it's a tool for real embedded engineers to start engineering solutions using embedded machine learning. That is the moment that we give real superpowers to everyone. Because no longer do you need to develop something as an embedded developer, throw it over the fence to a group of PhDs trying to find something in the data. You as an embedded engineer can start building these models. And that is the greatest thing. If our domain experts have this technology at their hands, that is the moment that we can really start solving real problems. And I think that's super exciting. So with that, I'd like to skip over to our demo. We have 2 amazing projects actually prepared for you, one with audio and one with vision. You can find these projects at edgeimpulse.com/NVIDIA. Actually, the full project will be there when this talk is being put live. let's get going. Right, so let's build a demo. So what do we need? Well, a Jetson Nano and a webcam, or a USB microphone. After that, log into your Jetson Nano and run Edge Impulse Linux. This will make that sensor available in Edge Impulse for very quick data collection. So let's go to our Edge Impulse project. And I now have under devices the Jetson Nano listed with both a microphone and a camera. So the first project that we're going to be building here is a bird sound classifier. Here I collect data from a number of birds. I mix that in with some noise, so data that is neither one of the birds that we're collecting here. And afterward we can train a model that can then distinguish those bird calls from each other and start counting them and, for example, send that to the cloud or process locally to do some proper bird counting. So the first thing you do here is you select your device. Here, my Jetson Nano. You select your sensor and your frequency and the label that we're setting. So we have both a house sparrow and a rose-ringed parakeet that we want to collect first. So you set a label, set a sample length, and fortunately I just hear a rose-ringed parakeet in the background. Beautiful. So after that, we have our data collected from the Jetson Nano in Edge Impulse, and I can play that back to hear the call of the rose-ringed parakeet. So we can do the same for the house sparrow. Once again, set the label, wait for a house sparrow to actually start its call. And beautiful, now we have that in Edge Impulse as well. So we continued this actually until we had about 45 minutes worth of data split over these three classes. Why is this noise class important? As I explained, a machine learning model tries to match the input to the output as best as possible. But if there's only two different outputs, either a rose-ringed parakeet or a house sparrow, every input will be matched to either one of those classes. And thus, if we hear something completely different, for example, no birds, it will still try to classify this as one of those two. So we'll need a noise class to help us there. From there, we can go to the impulse design, where we set up a pipeline, where we first cut up the data in 2-second slices. Then we'll have a pre-processing block, here a block that knows how to deal with audio, and turn that into a spectrogram, as we explained earlier on how we do feature extraction from audio signals. And finally, we have a learn block, where we add a classifier that's going to tell us how to distinguish between these three classes. So here's an example of this pipeline. We have the data here from the house sparrow, and here is the spectrogram that we generate. We'll always show on-device performance characteristics, and given that the Jetson Nano was so incredibly powerful, here you don't really need to care about that too much. We know we're going to be processing this, a full 2 seconds worth of data, in very, very little time. So the interesting part comes when we actually generate features for all of this data. One of the greatest things in the Edge Impulse Studio is the Feature Explorer. It's one direct view of everything in your project, your full data set, and how well it separates. So here we have the house sparrow, some noise, and the rose-ringed parakeet. If I remove the noise, I can start seeing some separation between these two classes. And if I see that they're not separating nicely, I can just click on stuff and play back a sample. Even though it might look a little bit mashed together, we can probably find a really nice line basically that split this data up. It doesn't have to be a single line, naturally. This is an ML algorithm. We don't need to program this out by hand. So I think this is going to work quite nicely. So let's go to our classifier and see how well it really works. So we have a number of presets that we can do here and that we can load in. The default one typically works nice, but you have full freedom in actually manipulating this. If you have a data scientist in your team, you switch to the expert mode. But here we trained our model and we get to about 92% accuracy, which seems great. Let's try this out on the device. So after you've trained a model, the only thing you need to do to actually make this run on the Jetson Nano locally is just run Edge Impulse Linux runner. This will build the model in Edge Impulse in the background, load full optimizations for your target. So we'll use TensorRT underneath, and then run it directly on the Jetson Nano. All right, so we'll see the raw data here. If something is above 0.8, that's probably the call from a bird. So let's see that and see if we can actually get a house sparrow to say something. And that jumps up nicely to about 1, indicating that we definitely heard something. So really easy to verify this model. So with our high-level SDKs, you can actually write a little bit of code that integrates this into your own application really, really quickly. So let me show you that with our Node.js SDK. So we can instantiate the audio classifier, and the audio classifier automatically attaches to a microphone, combines it with a model that you downloaded from Edge Impulse, and then gives you a very clean set of results from there. So we call start here. We inference 4 times a second, even though our window size is 2 seconds long. So we have an overlapping window automatically, which helps with accuracy. And when we have a result, we'll get the data in here. And as said, we think we see a house sparrow if it's above 0.8, 80% accuracy or confidence, or a roasting parakeet if it's 80% higher. And then from there, in this case, we can print the conclusion. So here we say there's a house sparrow somewhere, there's a roasting parakeet here. And from there, it's really easy to integrate this with your current service. Maybe you want to send it to Azure IoT or to AWS, or maybe even show it on a nice little dashboard to show how many of these birds you've seen. So to run this on your Jetson Nano, just run here the example, just a JavaScript file. Now it's listening, and our initial state is other. We do not hear either of these birds. But if I hear a house sparrow, wonderful, immediately detects. And let's see if we can actually get a roasting parakeet to say something as well. Wonderful, really quick. And as you can see, it is incredibly fast. So we analyzed 2 seconds full of audio live here on the Jetson Nano in about 20 milliseconds. So plenty of time to actually do something else with your time. Wonderful, really easy. I hope you get a quick idea of how easy it is to build these models directly on your Jetson Nano. And that's not the only thing we can do. Let's take it up 1 notch and build a model that can detect poachers and elephants based on the camera on the system. So for our second project, we are going to be using a camera connected to the Jetson Nano. Got a camera here. And the project that we're going to be building is a system that can detect humans as well as elephants. And if I see an elephant on camera, that is fine. This is a system I could deploy in the savannah to keep an eye on where elephants are actually going. And if I see a person in the shot, that is fine too. I mean, there's probably people on the savannah too. However, if you see both, that is probably a danger. It could be a poacher or it could be a danger to the human. So let's build a data set that can actually do that. So I have my Jetson Nano connected. I have selected the camera sensor now. And I get a live preview here of the camera feed. You can see me. Hello. So what do we need? Well, first of all, I need an assistant because I am going to be playing the human. So here I have with me Matthijs. He is one of our infrastructure engineers, and he's going to be clicking on the start sampling button for me. What I also need is an elephant. Naturally, we're in a studio. I couldn't bring a real elephant, but my son's toy elephant will do just as well. And of course, we need a person. So first, let's snap a couple of photos of the elephants. Matthijs. So we're going to position the elephant in front of the camera. I'm just going to snap a few photos with me out of the frame. Next, we'll do a couple of photos of me in the frame, so the system knows who a person is. And last, we'll do a couple of photos of both me and the elephant, because we can detect multiple objects. All right, there we go. We've collected some data. Let's label that data now. So we go to the labeling queue. And here we have all the photos that we've collected. And we have a really easy way of tagging the objects here. So I'll drag a box. I'll select elephant. And we actually have Matthijs here. Matthijs is also a person. So I'm going to label him as person. And I click Save Labels. And here we use machine learning to track these objects in the frame. And this makes it a lot easier for you to label this data automatically. Just click Next, verify that the box is set correctly, and go on to the next frame. You see here that I do something with the elephant. Let's actually change that box. There we go, really quickly labeled all of our data. So this leaves us with only 70 photos. And you might think that is not a lot for an object detection model, but we have a couple of tricks on our sleeve. So we can use a transfer learning model, and that is a model that is pre-trained on a much larger data set as a basis for this model. After that, we strip off the top layers of the model and retrain that with the data we just collected. This way, we can actually build accurate and well-working models with a fraction of the data needed, which is really great for these type of hyper-local problems. If you're doing manufacturing, you are probably not interested in having a model that can detect thousands of objects, but rather the thing you're interested in is something that can distinguish between whether a screw is screwed in or not, a hyper-local problem. And Jetson is perfect for this. Thanks to both transfer learning and our easy data collection UI, you can verify that these models or validate that these models work in mere minutes, and then from there use it as a proper engineering project to really build a model out. So once again, like we have in the audio collection data flow, we have an impulse here. Here it consists of an image that we resize to 320 by 320 pixels. We have an image preprocessing block, and we have an object detection block. If you just want to do normal image classification, you can add that by clicking Add a Learning Block easily. Again, we show the Feature Explorer to give an indication of how well our model separates. So here we have something from our previous data set, and I'm going to run our feature generation again to see how well our data separates. And we can probably distinguish the photos that were made in my house when I pre-did this video and the photos we just collected here in the studio. All right, so we actually see very clear patterns. We see a complete cluster of person data here in orange, and this is all data that was collected here in the studio, as you can see. Then we'll have another cluster of person data, and that's data that's actually collected in my house. Then we have an elephant cluster here, and another elephant cluster here. But the nice thing here is this data separates really nicely, and that means that our ML model will probably be able to learn how to distinguish this very, very quickly. So let's train our new model. Just head to the object detection page. We have a transfer learning model readily available here for you that will fit nicely on the Jetson Nano, running actually with about 50 frames a second with GPU enabled, which is astonishing. You can really do a real-time classification here. Click Start Training, and we're going to wait a few minutes. All right, so our model is now trained, and we can now run this model again on a Jetson Nano. So we go back, and through the Edge Impulse Linux runner, we can download this model for offline use. After we download this model, it is available completely local. So no internet connection required. So we hacked together a quick web server that shows us the image from the Jetson Nano as well as any of the boxes that we see, so we can detect what we see. Now, let me start that. So on my laptop, I'll go to the Jetson Nano at port 4911, and there we go, we have the image. It's a bit blurry. See it. There we go, and we have an elephant, and that is perfect. As said, an elephant alone, that is no problem. Also, if I'm a person, that is fine too. But problem starts the moment that we have both an elephant and a person in there, and that's the moment that we want to do something here. So I can open my editor, and once again, similar to how we do the audio classifier, we have an image classifier. And whenever there is a new classification, here we do it about 10 times a second, but you can do it a bit faster if you want to, we get a result, and we get the bounding boxes here. So what do we see? Do we see a person? Do we see an elephant here? If we find both an elephant and a person, that is the moment that an alarm is actually necessary. So, and because this is a really nice example in just Node.js, we can just use the Twilio API for that and send a text message, for example, when this happens. So in just a few lines of code, you can not just train your ML model and use it in your application, but actually couple it to other services to do alarms, for example, or do integrations with your own backend. So here we say, if both the elephant and the person are present, send a message, in this case, to my phone number that both are seen and that we are in danger. So let's try that out, shall we? So we have the elephant here, nicely detected by the ML model, and now nothing is going on. But what if a person actually walks in? And we get a text message straight away that danger is here. So that was it. This is how easy it is to build ML models that deal with sensor data with Edge Impulse and the Jetson Nano. So here in the last minutes, I'd like to have a small recap of what we've seen here in the last 40 minutes. First of all, I hope you realize that the ML hype is real. It's possible to use machine learning in the devices that you currently have to solve real problems, things that we could never do before on our edge devices. And the Jetson Nano, together with Edge Impulse, is the perfect place to get started. It's an incredibly powerful device. It's really, really easy to collect data from the real world in it, and it's fantastically simple to actually deploy that to the real world. And together with that, I hope that everyone unlocks their own superpowers by applying ML to your domain expertise, because that is by far the quickest way of actually transforming our society and transforming these 30 billion devices that ship every year into much more capable and more useful devices. With that, I'd like to thank you all, and goodbye.